Next, we're going to return to the London Eye Ferris wheel example. So first of all, we'll rederive the equation for the height of a passenger on the Ferris wheel as a function of time, just for the purpose of general review. So it's always useful to we'll kind of quickly derive that. So when we did the London Ferris wheel earlier, we saw that the diameter of the Ferris wheel was 120 meters, and that the height of the Ferris wheel was 135 meters. So essentially, the Ferris wheel looked like this, and then it was slightly off the ground like that. So this distance would be 15 meters, and the radius of the Ferris wheel would be, well, 160 divided by 2, 60 meters. So the midline is going to be approximately 60 plus 15, so 75 meters high. And of course the overall height is going to be 135 meters. So basically the trough of the sine or cosine function will be at 15 meters, and the peak will be at 135 meters, the midline 75 meters. Now a passenger is going to start at the bottom and move up like this, past the midline, move to the top, go to the top, and then start coming down on the other side. So if you think about the height of the passenger as a function of time, it will okay, let's do this again. Just kick that out. Okay, so if we think about the height as a function of time, it's going to look like this. So starts at the bottom, passes the midline, goes to the top. Actually, let me make that a little smoother. And then comes back down. Right, so this is the height of a passenger as a function of time. They start down at the bottom, the ride takes them up, takes them all the way to the top, right here, and then all the way back down. And the period of the ride is 30 minutes. So we'll say this is with respect to time, and this is h of t. So first we want to come up with a sinusoidal function that describes this. And then we have the midline, just use yellow. So there's the midline. So this is going to be 75 meters, 15 meters at the bottom, and 135 for the peak. Okay, so first of all, the midline is 75 and the amplitude is 60. Right, so we have 60 meters there and 60 meters there. That one is height is 75. So 135, 75, 15, a delta h of 60, delta h of 60. And also, we first, it's useful to say, well, what does this function look like, sine or cosine? Now, of course, sine and cosine are the same function. They're just shifted by 90 degrees from one another. But it's useful to, if it's more in line with either sine or cosine, to use the one it's more in line with, because otherwise, then you don't need a phase shift. Well, cosine, so let's review. Let's do it up here. Cosine, I can do them both at the same time. So remember, cosine starts at the peak, comes down, and then goes like that over a period of 2 pi. So that's cosine of x. Whereas sine of x starts at 0, comes up, comes down, and then comes like that. So that's sine of x. And you'll notice that if I were to shift sine of x 90 degrees or pi over 2 radians to the left, I would obtain exactly cosine of x. Well, this starts at not the peak but the trough, so cosine of x seems like a good thing to use. And instead of using a shift, let's just use a negative sign. So instead of cosine of x, we can do the negative cosine of x. So if this is cosine of x, negative cosine of x is just a reflection, so that one is negative cosine of x. So negative cosine of x flips cosine of x over the x-axis, because instead of having plus whatever, I get minus whatever. Instead of plus 0.9 as the output, I get minus 0.9. So this looks in line with negative cosine. So we can start by saying we have h of t is equal to midline, which is 75. Instead of plus, I'm going to use minus the amplitude cosine of inside something times t. And because it's already set up the way it is, we don't need any phase shift, so I just have to figure out the angular frequency. Well, it makes a complete period, as a complete revolution, in 30 minutes. So the argument of the cosine function, so the stuff in here, has to increment by 2 pi when t reaches 30. So 2 pi over 30. That way when t is equal to 30, 30 over 30 cancels and you just get 2 pi. You've made your first revolution on the Ferris wheel. You've gone one exact period. So that is the height of a passenger in the London Eye Ferris wheel model as a function of time. So let's write that up here. H of t is equal to 75 minus 60 cosine. And instead of saying 2 pi t over 30, let's say pi t over 15. So this is the height as a function of time. Now we want to take the derivative of this and compute at what rate is the passenger's height or the altitude, at what rate is the passenger's altitude changing as a function of time. So to do that, we just take the derivative. So there's h of t, h prime of t, derivative of 75, 0, and then now we have to take the derivative of the cosine function. So then we get 0 minus 60. Now we have one of these composite functions, so it's cosine of something. So when we take the derivative of cosine, we get negative sine. So it's going to be negative sine of something. So we just keep this stuff inside. So the derivative of cosine is negative sine, and the negative canceled out the other negative, so we get plus 60 sine pi t over 15. And now we multiply to correct, because we're not taking the derivative with respect to something, we're taking the derivative with respect to t. So we need to correct by multiplying by the derivative of something with respect to t. So the derivative of this inside function with respect to t is just pi over 15. 60 over 15 is equal to 4, so h prime of t is equal to 4 pi sine of pi t over 15. So what does that look like? So this is a sine function. It's going to satisfy the general shape of a sine function. The period is 30 minutes, the same as it was with this period up here. And then the amplitude is 4 pi. So it's 4 pi minus 4 pi. And the midline is 0, because it's not 5 plus 4 pi sine of pi t over 15. It's just 4 pi sine of pi t over 15. So the amplitude is 0, which means its midline is 0, which makes sense because half the time you're going up, the other half of the time you're going down. So back to, the Ferris wheel. For your first 15 minutes, you're going up. And for the first 15 minutes here, this is h prime of t. The derivative is positive, meaning the height or the altitude is increasing. For the next 15 minutes, you're moving down. So it makes sense that h prime of t should be negative between 15 and 30 because h is decreasing, the altitude, you're moving down, so the derivative is negative. And also note that initially the rate of change of your altitude is 0. That's because initially when you're at the bottom, your velocity vector is to the right, it's horizontal because you're moving along the rim of the wheel. So when you're at the bottom, you're just moving this way. So you don't have any increase in height. And then as you start to go along the circle, you start to increase in height faster and faster. When you're at this point, you're increasing in height at the fastest rate. And that happens at 7.5 minutes, which would be right here. And of course, you're decreasing, your height is decreasing at the fastest rate at the counterpoint on the way down. So that would be at 22.5 minutes. That shows us how to model the rate of change of your height as a function of time when you're riding on a Ferris wheel, using the derivatives of sine and cosine.